So let's get started. Real quick, before we officially get started, I want to just say a couple quick things. This is our first time doing any sort of like virtual workshop like this. We're super excited to have you, and we're gonna do our best to sort of make sure the logistics go smoothly and stuff. But please, we're just going to ask you to keep yourself muted. I think everyone is muted by default right now. And if you want to say something or ask something, there'll be some points for questions. Try to save the questions until I say do you have any questions, or there's like a slide. And if you want to add something, we'll have some points of interaction. Please make use of the raise hand feature. So you'll be able to click on participants at the bottom. And then you'll see a raise hand feature, and then we'll be able to see it and we'll unmute you. So yeah, again, Stanford students, if you're here for the Stanford summer session and you want to receive some credit, just go on this link, enter this password in your email. And finally, we're going to do some exercises and stuff. We're going to try to keep this kind of interactive. So feel free to open up that Colab link and you'll be able to follow along as I do some live coding and hopefully not embarrass myself. Okay, so with that, I want to welcome you to AI for Social Good. This is our first time that we're going to do this sort of workshop. We're super excited about this. We actually started this course a couple of years ago as a Stanford course, and now because of COVID, we're going to try to democratize this to anyone who wants to come and learn about what we teach, and we're super excited about that. And just introduce myself. Hi, my name is Shubhang. I'm an incoming master's student at Stanford. I did my undergrad there as well. I'm very focused in AI in terms of doing a lot of research in academic and industry research labs in AI. My focus is sort of in computer vision. I've also done a good amount of teaching, including this course. And I started this course with my friend Karan, who's also on this chat. So you want to introduce yourself, Karan?
Hey guys, I'm also helping organize this workshop series. I also helped bring this course to Stanford with Shubhang. I'm now working as a research engineer at Google. I work on privacy-preserving technologies like federated learning. Happy to be doing this with you guys. So hope you have a good session.
Cool. So the way that this series is kind of split up is we're going to have three workshops in the series. The first one is today. Welcome. So today we're going to talk about deep learning. Next week we're going to talk about computer vision, and the week after we'll talk about NLP. The way that it's sort of formatted is we have sort of 30 to 45 minutes blocked off at the beginning where I or Karan will give a short lecture, which gives y'all some theoretical backing in terms of machine learning. And then we'll transition into a research talk from an invited speaker. And today we have Pranav Rajpurkar, who's a PhD student at Stanford, and he's going to share some of his research. So let's get into the content. Actually, before that, I want to say thank you. Thanks so much for coming. This is, like I said, the first time we're doing something like this. We have folks from not just Stanford, but from all across the country, from UW, Brown, NYU, Harvard, Berkeley, ASU, U of I, and a lot more, just to name a few. We have some international students as well from University of Sao Paulo, from Oxford, from McGill. And I think 25% of y'all are not even college students, which is very exciting. Whether you're a high school student, trying to do something fun during this boring summer, or someone who's working full-time who wants to learn something new, or a college student, whether from Stanford or elsewhere, we're super excited to have you. We're glad you're here learning with us. And we hope that we do the best that we can, and y'all walk away learning something interesting. So thank you. Okay, now let's get into the content. So why are we all here? Why are we talking about AI for social good? And why is it important? Let's take a step back. Why has machine learning seemed to take off recently? It seems like machine learning has become a really hot topic within CS research and CS application in industry. And why has this happened recently? So as it turns out, neural networks are really good at modeling complex data very simply. So we can have data which is very complicated, and we can very easily gain insights from this data using relatively simple operations. And we'll talk about exactly what operations those are and what constitutes a neural network. Okay, so in addition to that, we have a lot of data. We have a lot more data than we've really ever had. Because of the internet, we have so many images, so much text, a lot of it unlabeled, So we don't really know what to make of it, but we can label this data. We can use unsupervised machine learning techniques, which don't require labels. And we can get a lot of insights from this cornucopia of data, which is the internet. We also have a lot more compute. So with the rise of GPUs, we're seeing that we can train models, bigger models, faster. And that really helps push the cutting edge. And the research community has all sort of taken hold around machine learning. And as a result of that, we're seeing better and better models and better training techniques along with it. So we're always beating some state of the art every time a conference comes around. And because of this, we're seeing a lot of low-hanging fruit getting grabbed. So before, folks never thought about applying machine learning to medicine, for example. And now Pranav is going to talk about how he has applied deep learning to medicine and how that field has evolved over just a few years. And this is just one of the many examples of applications that had never been thought of applying machine learning to, and now we're seeing great results of machine learning models on these use cases. So I'm going to go through a couple of those right now. So predicting crop yield. Say that we have a map and some sensing data. We can pass that through what's called a convolutional neural network. We'll talk in about a week about what all that is, and we can use that to predict crop yield within certain areas, and this is super important for agricultural industries. Triaging mental illnesses. So this crisis text line uses NLP to understand who's most at risk and who needs intensive care right now in terms of the customers that they're serving. Predicting poverty. There's a lot of areas that don't get a lot of census data or some sort of measurement of how many resources need to be allocated to those regions, just because we don't really know who lives there because of various restrictions when it comes to measuring who lives there, what they need. And so a team from Stanford actually predicted poverty from satellite images. And so that better helps allocate resources to those areas. And another team from Stanford, in fact, a team which includes Pranav, he'll probably talk about this along with a lot of other things, a lot of projects that he's worked on. They used a convolutional network to detect arrhythmia. So using this heartbeat data, they can predict who is suffering from arrhythmia. And that's very useful for the medical field. And these are just a few examples. So this doesn't come without its problems, though. In fact, we see a big issue of bias within machine learning models. One of the biggest causes of bias is biased data. Data comes from society, and society is biased. And we see garbage in, garbage out. If we have biased data, then anything that's trained on biased data will downstream be biased in and of itself. And especially in like consumer-facing or user-facing applications, we don't want to see that. Engineers, we really care about pushing the cutting edge. We care about metrics. We care about getting state-of-the-art. But we don't care about what happens. Like, we don't care about the end-to-end scenarios. For example, next week we'll talk with Deborah Raji, another research scientist, about facial recognition. Engineers are really great at coming up with facial recognition technologies that are better and better in terms of accuracy. But who's going to get affected by this? Who are the minority populations who are going to be continued to be over-policed and oppressed as a result of these discriminatory facial recognition systems? This is something that we ought to care about because we build this stuff. So we have the power to stand up for those folks if we want to. In addition, we see that machine learning models are better and better at creating fake news, whether it's creating a fake video of someone saying something, a fake voice, fake text that seems like it's written in their voice. We actually have the power to create that stuff right now, literally right now. And we see that fake news is an issue even without AI. This is an issue which can be incredibly disruptive to democracies, especially with an election cycle coming up right now. This is something that we need to be cautious of. And of course, there's a lot of long-term risks associated with AI. I'm not going to talk too much about AGI because it seems far-fetched right now. But the thing is maybe these are considerations that we ought to take right now as opposed to when we get there. So let's talk about some problematic examples of AI applications. So a team from Stanford not too long ago actually used a machine learning model to predict someone's sexuality from their images. So I'm not even going to talk about how problematic this is. But of course, this could be used to further oppress homosexual folks, in which it's actually illegal to be homosexual in certain countries. Additionally, this paper is actually riddled with a ton of technical issues. It turns out that the majority of the predictive power of the model can be explained by differences in poses. So folks who self-identified as straight versus who self-identified as gay happen to just pose differently, just as a sort of trend. And that's like, you could actually recreate the predictive power of the model just by like changing the way that you sort of pose with your face. So this is actually just a flawed experiment altogether. There's a lot of moral considerations around self-driving cars. You might have guessed by now that the folks who are able to actually drive these cars on the road are sort of the upper echelon of society when it comes to income. But the folks who might be most affected by it are the opposite. It's important to realize that when it's comes down to a scenario where someone might get hurt and someone might not get hurt, might be saved by the technology in self-driving cars, there's a huge inequity which follows societal inequities, and we ought to think about that. And here's probably one of the most problematic examples of AI being applied to a consumer-facing application. So this Google Photos app, which was actually shipped to users, grouped together pictures by the main object in the picture. And as you can see, it labeled Black folks as gorillas. And this is incredibly racist. And the reason why this happened, as it turns out, it was disclosed later, was because there weren't enough darker skinned folks in the data set that this model was trained on. And it led to this incredibly offensive scenario that Google had to immediately mitigate and apologize for. So those are sort of all of the scenarios that I wanted to talk about. There's quite a few more. And I'm going to dive into a specific scenario in which we can imbue a model with bias relating to what's called word vectors. So today I'm going to talk about what word vectors are. We're going to talk about how we can use a model to uncover word vector bias, and how we can train said ML model. So we're going to sort of learn a little bit about the soft side of things, like how word vectors are biased, and then we're going to learn about some technical aspects of this project. So what are word vectors? Word vectors are essentially a numerical representation of words. So machine learning models work with numbers, and they don't work with strings. They don't work with words. So we need to represent words as numbers. But we'd also want them to not just be arbitrary numbers. Maybe they should sort of have some sort of meaning. So here we have an example of a two-dimensional word vectors. And here an interesting property is that sort of similar words are grouped together in similar regions. So anything that has to do with sort of like appliances or bathrooms, that sort of thing, is over here. Anything that has to do with tools and whatnot is over here, and you can continue to look all you'd like. And again, don't really worry about like how this is trained. How do we get this word vector model? Don't really worry about it. Just kind of assume that it's already there. It's already been trained. We'll talk about how to train a word vector system probably in week 3. But right now, just assume that it's there and it has this property. It also has another property. In general, we see this sort of arithmetic that we can do with word vectors. So here, the vector that we obtain from subtracting woman from man is the same as the vector that we obtain from subtracting queen from king. So that's pretty cool. This is sort of like an analogy that we can draw, like man is to woman as king is to queen. So that's pretty neat. It's gained some sort of understanding of the world and how it works. However, this is a very not good analogy that we can draw, which is man is to woman as programmer is to homemaker. So this is incredibly sexist, and this is actually exhibited. It was exhibited in the first version of Word2Vec, which is a really popular word vectorization model. And why do we care about all of this? So remember, garbage in, garbage out, right? If we have a model which uses word vectors, then we're going to have a biased model. And it turns out that all of these and many, many more user-facing applications use word vectors as their basal way of encoding words. So anything that has to do with like text or words, like anything like that, in these and many more user applications, use word vectors. And if we don't de-bias our word vectors, then we're going to get a biased model. Cool. So any questions on this so far? Again, use the raise hand feature. If not, then yeah, there's a question from Kamal, I think.
Normally when you have word vectors, would you want to create like a one-to-one encoding with like, say like a word and a number, because like words are like a finite set, so you're never going to run out of numbers, and then would you want to normalize them?
Yeah, so we don't explicitly require that the word to vector is mapping is a one-to-one mapping, but usually that just ends up being the case because here I've shown just a two-dimensional word vector encoding. Word vectors are actually like on the order of 300 dimensional. So it's very difficult to have two words be exactly mapped to the same space. So usually we don't see that, but we don't enforce that either. In terms of normalization, we don't really enforce any sort of like normalization in terms of the size of the space or anything like that.
Okay, but all the numbers that the words are encoded to should be between 0 and 1, right?
I don't think so, actually. Karan, correct me if I'm wrong, but I don't think that there's any limitation on or bounds on the numbers.
Okay, I was just wondering about gradient descent.
Yeah, we'll get there, but yeah, I don't think that this has an effect on gradient descent.
Okay, thank you.
Cool, thanks for the question. Okay, so we're gonna jump into some exercises. So here I have pre-downloaded some word vectors. These are called, y'all can see my screen, right, by the way? You can see my code. Thumbs up. Okay, so I have pre-downloaded these word vectors called glove vectors. These are just one type of word vectors. There's other types. One is called word2vec. If you want to learn more about glove, you can click here on the link. But just like I said, let's just assume that they're there. They've been trained. They have some useful properties. We have this helper function, which basically gets a word vector given a word. And we have this function to compute cosine similarity between two word vectors. So you'll probably recall cosine similarity from linear algebra. It's just a metric which tells you like how similar two vectors are, essentially. So we see that when we compute cosine similarity between good and great, it's higher than when we compute cosine similarity between good and human. And I guess that makes sense because good and great are more similar words than good and human. So does anyone want to like propose any more words to try out? Feel free to shout anything out right now. Anyone? Yeah, I think someone had raised their hand.
Yeah, could we try good and bad?
Sure. That's actually a good one because it comes out with an interesting result. So good and bad also has a high similarity. And the reason why that is actually you would think that opposite words have low similarity, but it turns out that they're used almost interchangeably in everyday language, right? Like it's just as easy to say that like that movie was good versus that movie was bad. So it turns out that those two words, although they're polar opposites in terms of meaning, they have almost identical contexts. So that's why they're very similar word vectors. I'm really glad that you actually came up with that example. Thanks. Okay, let's move on unless someone has a really pressing one.
In the chat, like corruption in politics.
Oof.
Yeah.
Juicy. It's pretty high. I'm not going to say anything. I'm just going to say that it's high. Okay, let's move on for now. Thanks for the suggestions, y'all. Okay, so how bad is this problem, right? So I made the claim that there's a lot of gender bias within word vectors, but how bad is this problem really? So we're going to use a model to uncover word vector bias. So here's what we're going to do. Here's the sort of setup. We're going to create a female-ness classifier. So given a word, this word vector up here, we're going to pass it through some type of model. We'll figure out what it is later. We're going to get a number as an output. We're going to call that y hat. This is our prediction. And this number is going to be between 0 and 1. The more female that the model thinks that this word is, the closer this y hat should be to 1. So what we should see is the answer for word vector for female should be close to 1. And the word vector for male should be close to 0. Right? This is what we would like to see. Then we can probe our model and see what y hat it gives for homemaker and programmer and et cetera, et cetera. So this is sort of what we want to do. We're only going to train our model on words where we have an appropriate association with gender. So words like female, male, woman, man, et cetera, where we know that it's okay for it to be associated with a certain gender. And we know the answer to. And this is called the ground truth, or y. So we know that female should be 1, male should be 0, woman should be 1, man should be 0. boy, girl, etc., etc. And we're not going to train our model on anything else, just these words. And then we're going to see what happens for these occupations and that sort of thing. And before I continue, you might be wondering, like, why are we doing this? Like, why are we coming up with a femaleness classifier? This seems like a strange thing to want to do. Yes, this is a toy example. But the thing is the upshot is we're not really doing anything wrong, right? Like, our data set is all like kosher words with associations with gender that we all know are like not bad. However, we're going to see that even when we train our model on just these words, we still get bias. And I'm going to prove that to you by doing some examples. And that should sort of show you how easy it is to accidentally imbue your model with biases, even though we're not trying to, and we're not doing anything explicitly wrong. Okay, any questions so far on what we're trying to do? Okay. So here's our model architecture. We have this 300-dimensional word vector. Let's act like each of these white circles is a number. I have left out all 300 circles, but you can act like they're there. We're going to pass it through a model. Right now it's a black box because we don't know what it is. And we're going to look for y hat, our prediction. Okay. So anyone have any ideas on how we could take these 300 numbers and get one number at the end? You may have any ideas on what we might want to do? Free to raise your hand. If not, I can just spoil it. Okay, I'm going to spoil it. So we can multiply each of our word vector numbers with another number. Okay, and then we just add it all together. Okay, and sometimes we like to add this b thing too. This an additional number which we just add on at the end. And that's going to be y hat. So y hat is going to be this number times w1, this number times w2, etc., etc. Add it all together, add b, and that's going to be y hat. Okay, this is called weights. These are weights, and this is bias. That word bias has nothing to do with like bias word vectors, bias models. That's an unrelated word. It's just called bias though. So, and altogether, weights and biases are called parameters. So we have a parametric model essentially, and it's parameterized by all these weights and this bias. And you might be wondering, like, what the heck? What are the weights? What is the bias? We'll get there. Don't worry. So, but let's just act like it's there. And essentially what we do is we do this dot product, right? You might remember from linear algebra, multiplying two things and then adding it all together. That's the same as, it would be the same as taking the dot product between this word vector and a vector which contains all of the weights. And if we take the dot product between those two, then we get the weighted sum between those two things. And then we add bias at the end. And that's our y hat. And just to be clear, this is our prediction value. These are our weights, the weight vector. This is our input, the word vector. And this is our bias value. This is just a scalar. And this is called linear model. This is a linear regression model. Okay. Any questions on this so far? That might have been a lot. So feel free to ask any questions right now. Okay. Okay, so we'll move on for now.
I have a question about the first thing that we were doing with like the two words. So is the number, like, you know how like the bigger it was, the more similar it was, the two words were?
Yeah.
Is that number like, how do we get that number? Was that from like how close they are on the grid?
Yeah, that's a good question. So we're computing cosine similarity, and here you can see the equation, or at least the code equation. So we're just taking the dot product between the two words, and then we're going to normalize it by the Frobenius norms of the two words, essentially. So it's bounded between 0 and 1. So the closer it is to 1, the more similar. So two vectors that are exactly identical would have a cosine similarity of 1, and two orthogonal vectors, so two perpendicular vectors, would have a cosine similarity of 0.
Got it.
It's bounded between -1 and 1, right? So I guess two anti-parallel vectors would be -1, I think.
Okay. Wait, so then it's possible to get a negative number as well?
Yeah, it can be between -1 and 1, essentially, because we're normalizing the numbers.
So would like a negative number actually be like a bigger difference between like the two words?
That's a good question. I think when it comes to an intuitive understanding of word vectors and cosine similarity, I'm not so sure how much weight the sign has. Honestly, like I think the direction is really what matters the most. Like the direction of the vector is really what matters the most. So whether it's negative or positive, I think doesn't matter. I think the magnitude of the cosine similarity is, I think, more important. That's a
Okay.
good question.
Sorry, his last question. Could you give like an example of like what would be like a negative?
Oof. Gonna put me on the spot. I have no idea. I'm gonna defer to Karan. Do you have any example? Do you have any ideas?
I think if we try to pick two really, really different words, it should be negative. It could be close to 0 as well. We can try to come up with some idea.
Super different words.
Maybe like antelope and corruption.
Antelope and corruption. Okay. Let's see what happens. Oh yeah, that's negative. Nice. That's a good one. Yeah, so I guess maybe that will tell you that they're completely different. There's like no relation between them.
Mm.
But again, I would focus on the magnitude. The magnitude is sort of the more like intuitive, sort of has a more intuitive lending to it.
Okay, thanks.
Yeah, of course. Any other questions on this or anything that we talked about since then? Okay, I'm gonna move on just because of time. One thing to note is that our y hat is not bounded between 0 and 1 here, right? These can be any numbers, these can be any numbers, and this can be any number, so y hat can be anything. So we're gonna bound our y hat to be between 0 and 1 by squashing everything between 0 and 1 using what's called a sigmoid function. Here's what it looks like. Anything that we give to the sigmoid is gonna be at most 1 and at least 0. So as z tends to infinity, sigmoid of z tends to 1. And as z tends to negative infinity, sigmoid of z tends to 0. So no matter what we give sigmoid, we're always going to get between 0 and 1. So now we're going to change our linear regression model to a logistic regression model. So we're going to have y hat, again, the prediction is equal to sigmoid of weights times input, which is a word vector plus bias. Again, we haven't talked about how we're going to get weights. We haven't talked about how we're going to get bias. But now we have everything between 0 and 1. And the reason why we want this is because we can think about this as a probability now, right? Like this is sort of represents the probability of femaleness according to the model. And probability can be between 0 and 1. So yeah, any questions on that? Why we want to do that? Okay, so let's do some cool exercises. I'm gonna do some live coding, also known as me embarrassing myself. So here is a sigmoid function written up here. So does anyone want to sort of guide me through what I should do? Sigmoid of z. What are we going to do? I'm going to start off 1. Didn't even do that right. 1. Chat. Anyone have any ideas? If not, I'm going to keep. Okay, yeah. Let me unmute you. Yes.
Yeah, you could do 1 divided by, and then in parentheses, 1 plus
some x function, right?
Oh yeah, we could do that. Yeah, and then if within parentheses again, we could do I suppose x is the parameter, so negative x.
Cool. Yeah, actually our parameter is negative z. Is z.
Oh, sorry, that's a z.
Yeah, and we're going to use a package called numpy to do all this. So we're going to do np.x. Awesome. Good call. Now we're going to compute logistic regression. Remember, this is what our prediction is for logistic regression. We're going to use a word vector, which is x. I'm going to get that real quick. Word vector is equal to, we're going to use that helper function, get word vector, word. Cool. I'm going to go ahead and do this since we're running out of time. Sigmoid of w times word vector plus b. Okay, and this, we can't do it that easily. We have to use this numpy function, np dot dot, and this takes the dot product between w and b and a word vector. Okay, cool. And watch this, guys. So I'm gonna copy and paste the answer in case I made any typographical error. I don't want to hold everyone up, so I'm gonna just copy and paste the answer. That feels good. I think I did make an error, in fact, so cool. Okay, there we go. So we have our sigmoid function, we have logistic regression function computed. Now let's figure out how we're going to train this thing, right? Like what's W, what's B? So remember that we have the correct answers, right? Like we know that for female it should be 1, for male it should be 0, etc. So maybe we could use those answers to sort of inch W and B in the right direction. Like maybe if we're supposed to say 1 and we're saying like 0.2, we ought to say to the weights and biases like, hey, you got to move a lot because we're really, really off right now. Or if we should be predicting 1 and we're predicting like 0.9, maybe we can say, hey, you're a little off, but you're doing pretty good, so just change a little bit. So we ought to have some sort of number which tells us how bad we're doing or like how off we are. And this is called loss. So this is a measure of wrongness. We compare y and y hat, the prediction and the ground truth. And this number tells us how bad we're doing, and we minimize that number, right? So in essence, by minimizing how bad we're doing, we're increasing how good we're doing, right? Do you see how that makes sense conceptually? Cool. So what are we going to have as our loss function? How about this? Let's maximize this. So this looks complicated, but let me break it down. So remember that y can be one of two numbers, right? Y can be either 0 or 1. This is the correct answer, right? In the case that y is 0, this entire expression simplifies to 1 minus y hat, right? And when we maximize 1 minus y hat, what are we doing? We're minimizing y hat, right? Because y hat can be between 0 and 1. So to maximize this, we essentially are minimizing y hat. And by minimizing y hat, we're bringing it close to 0, which is our ground truth, which is great. We want our prediction to be close to the ground truth. So that makes sense. That checks out. In the case where y is equal to 1, we're maximizing y hat itself. And again, since y hat can be between 0 and 1, by maximizing y hat, we're bringing it as close to 1 as possible. Again, we want that to happen because that's the correct answer. Does that make sense? So in both cases, we're pulling y hat, our prediction, to be as close to the correct answer as possible. Okay. I'm going to make this a little bit more complicated by saying instead of maximizing this, we're going to minimize this. Okay, hold on one sec. So minimizing this, we're going to do this is because this is the negative log of what was on the previous slide, right? So this is the same as this, just to be clear. We take all this whole big mess, we take the negative log of it. Log is monotonic with x, right? So log of x, maximizing log of x is the same as maximizing x, okay? So that's fine. But then minimizing negative x is the same as maximizing x. So minimizing the negative log of something is the same as maximizing this thing itself. Okay, that was really complicated. So I'm going to open it up to questions. This is essentially our loss function. This tells us how bad we're doing. And by minimizing this, I claim that we're going to make our model better and better. Any questions? Yeah, I think question from Evelyn.
Yeah, what's the purpose of the log?
Okay, yeah, that's a good question. So why not just minimize the thing itself or maximize the thing itself? So log is actually more numerically stable, so that helps out with that. In addition, there's also like a big theory around why you should use log. It's actually a really nice like machine learning theory. I'm not gonna talk about it at all. It's sort of outside the scope of this workshop, but it's there. But it doesn't harm us to do that because, like I said, log of x is monotonic in x.
So you wouldn't, you would never have y hat be 0 or 1, right?
Y hat, it's okay if it's 0 or 1, right? Because if it's...
Well, because then it would be undefined.
What was that, sorry?
Because then the loss function would be undefined.
Yeah, so I mean, one effect of the sigmoid function is that the output ranges from 0 to 1, but it doesn't include either 0 or 1. So you're right that it'll never happen. And so this isn't a worry with our loss function.
Yeah, that's a good point. Yeah, actually, that's a good point. Because y hat, if it's 0 or 1, then this is undefined. Yeah, that's a good point. Yeah, and the good thing is it only gets to 0 or 1 at infinity or negative infinity. So we're never going to get there. Good question. Okay. So if there's no more questions, unless someone has any questions, I can move on. Okay, so how can we minimize this? Any ideas on how we can minimize this function? I've said this term a couple of times so far, in case you were listening. So I'm just gonna go ahead and spoil it. So we use this process called gradient descent. Remember from linear algebra, the gradient of a function tells us essentially the direction of maximum increase. So let's say that there was only one weight, and then we can plot the loss as a function of the weight. And at any point, we can get the gradient, and that'll tell us what the direction is of maximum increase. If we go in the opposite direction, then that's the direction of maximum decrease, right? So we can take the gradient at this point. It tells us where to go. We take a small step in that direction, and then we compute gradient again. It tells us where to go. We take a step in that direction, on and on. We keep doing that until we reach a gradient of 0. That tells us that we're at least at a local minimum, if not the global minimum. In multi-dimensional space where we have not just one weight, but billions of weights, we see a lot more saddle points than cusps. And as a result of that, it's actually very difficult to get stuck in the local minima. It's a lot more common if you're seeing a gradient close to 0 that we're actually at like a local minimum or like a close to the global minimum essentially. So the problem of getting stuck in local minima is not as big of a problem as it turns out in practice. Yeah, there's a question.
Yeah, I had a question. Why do we do gradient descent instead of just taking the function and calculating where the gradient is 0 and using that to find the minima, and also doing the second derivative to prove that that critical point is a minima?
Yeah, great questions. Those are always the first questions that people ask. It's super easy to do in two-dimensional space, right? It's super hard to do in billion plus dimensional space. That becomes incredibly computationally expensive. It's cheaper to do what seems like this strange iterative process. It's much cheaper, and it actually gets us to a pretty good minimum anyway. So that's the reason why we do this process instead. Good question. Any more questions? Oh, also, yeah, what Evelyn said, there's no closed form solution for logistic regression. Yes, there is a closed form solution for linear regression, but not for logistic regression. So you can actually jump to the minimum. Cool. All good points. Okay, a couple more slides and then we're gonna get to some examples.
Could you go over momentum really quick if we have time?
We will try, but that might be outside of the scope of today's lecture. We'll get to that maybe next time, but we'll try. Okay, I'm gonna move on real quick. So just to sort of formalize what we have been talking about intuitively, we have a weight, which is right here, W sub I. We get its gradient, which is this thing, dl dwi. And then we move the weight in the opposite direction of the gradient, which is why there's a minus here. And we scale that step by this alpha. Alpha is called the step size, also known as the learning rate. And the reason why we do that is because we don't want to just step using the raw gradient magnitude. We want to sort of scale it. It's in fact important to choose a good learning rate, because if it's too small, then we'll inch towards the minimum and it'll take a long time. If it's too big, we'll bounce right out of the minimum and we will never reach it. But if it's good, we'll get there in a good amount of time. And it's okay. So the TLDR, we compute the loss by comparing prediction and ground truth. And then we try to minimize that loss by changing W and B using gradient descent. So that was a lot. So any questions on this so far? And I'm going to do some sort of examples in code right now, and maybe that'll build some intuition as well. But before that, any questions? Okay, let me move on to the code then. So here I'm going to compute the loss function. So I'm going to do the first part, and then maybe someone can help me out with the second part. So we're doing 1 minus y times np.log 1 minus y hat. This is the first part of our loss function. Maybe I should back up and talk about exactly what this is. We're going to loop through the entire training set. And for every example, we compute our y hat, which is our prediction, using the logistic regression function that we wrote earlier. And then we're going to compute the loss relative to y hat, which is the prediction, and y, which is the ground truth. And in case you want to see the training data, here's what it is. These are all words that are like appropriate to have gender connotations. Nothing necessarily problematic in here. Okay. So coming back to this code, anyone want to finish this up for me? I can also do it. I'll just do it. Plus y times np.log. And this is just a loss function that we talked about earlier. This is what we derived from first principles just a few slides back. Okay. Here we've computed the gradients. I'm not going to go into the math of why this is the gradient. Just assume that it is. We'll probably talk more in depth about that in our next workshop. but here's what they are. Can someone tell me how we can use this gradient to update the weight? Can we have this learning rate?
We could replace that 0 with the gradient of, in this case, d weights times the learning rate.
Yes, perfect. Well done. And I'm going to do the same thing over here with d bias. Okay, and again, I am going to copy paste the correct answer. There's no man behind the curtains. I think that was correct. Cool. Now let's see what happens. Let's train this model. We're seeing that our loss decreases. Cool. So that's what we like. That's what we like to see. Now let's see what it does on words. This model does predict that she is female and he is male. So this is fine. In fact, this was in the training set, so it's good that we're seeing this being correct. However, let's see what happens when we run our model on these words which should not have gender connotations. Okay, yeah, so this is not looking too good for us. Nurse is female, artist is female, genius is male. This is interesting. Chef is male versus cook is female, boss is male, etc. It seems like every single one of these professions has attached to it our stereotypical thoughts on what these occupations, how they're associated with gender. Remember, this is, where is it? This is all that we trained our model on. None of those professions are in the data set, right? Like we haven't done anything problematic in terms of training our model with bad words. Even so, we've learned a really negative and sexist model. So this is what I've been trying to say and show, is that it's very easy as an engineer to end up learning something and maybe even deploying it to the real world, something that is imbued in stereotypes and sexist connotations.
So if we didn't train the model on those words like nurse, homemaker, then how does it even recognize those words? And like, shouldn't it be, well, yeah, like how is it knowing that?
Yeah, good question. So this is what we call like inference, right? So we train our model on certain words, and then we can use our model to predict new words that it hasn't seen before, and that's called inference. The words, although the model has never seen these words before, it has seen that format, right? Like it has seen a word vector. So it understands how a word vector works. It has learned something about word vectors. And so it can take a new word vector, which it has never seen before, and do some sort of prediction with it. And although our word vectors were sort of gendered words, we can still do prediction on non-gendered occupations and still sort of understand what the model understands about those words, essentially. Does that make sense?
A little bit.
Okay. Long story short, we've trained a model which can take a word vector and predict gender. And we've trained it on word vectors that are associated with gender. And we've used that to predict gender of word vectors that it has not seen before. And since it's able to take word vector and output gender, it can take any word vector, including ones it has never seen before, and output prediction of gender. Make sense?
Maybe a way of getting at the question as well is also, I think the intuition is like we haven't even looked at the word nurse or homemaker. So where does this come from?
Mm-hmm.
The intuition is these word vectors were trained on a really large corpus of text, where you're looking at co-occurrences between words like nurse and other words associated with gender and stuff like that. And so that corpus must have encoded this information because we didn't include it anywhere else while we were doing this. And so the idea here is basically this corpus is basically used to train a bunch of different word embeddings, which are used in a bunch of different places. We seemingly innocently have just tried to use it for something where we didn't explicitly do anything bad, it seems like, and yet it seems to reflect all these biases.
So it's almost like an outside source of data. Like, what do you mean by corpus? Like body?
Yeah, so the way these word vectors are trained, by the way, we'll get into this in 2 weeks, but the way these word vectors are trained is generally such that kind of co-occur near each other in a body of text like Wikipedia tend to have similar word embeddings, or tend to co-occur with similar words to have similar word embeddings, and words that co-occur with different words have different word embeddings. So that's why words like cat and dog have similar word embeddings, even though we never trained them. We never actually did anything ourselves. And so if you ask the model also, like, if nurse and female is more similar to nurse and male, you'll also find that nurse and female is more similar. And so it was encoded in the word vectors, not anything that we did before.
Got it. Okay.
We're going to move on for now, but if anyone has any questions, please feel free to email me. We just want to make sure to get to Pranav's part of this presentation, so we're going to move on for now. But these are all really good questions. I'm going to wrap this up with one last thing. So what exactly is a neural network? You're probably here to learn about deep learning, learn about neural networks, and it's like, we never even talked about it. But it turns out that we did. This is a neural network. Logistic regression is a very simple neural network, in fact. Anytime that we're doing some sort of multiplicative and additive operations with some sort of vector or array input, and then we're using that to get some sort of prediction, we are using a neural network, essentially. A deep neural network has more weights, essentially, and more nodes. So we can transform our 300-dimensional word vector into a 200-dimensional hidden vector, and each of these arrows represents a weight. So we have 300 times 200 weights. We have 200 biases, essentially. And we train all of this in the same way that we talked about with logistic regression. The only difference is we have a lot more parameters. So this is a deep neural network, essentially. So quick summary, we learned that AI has been applied for a lot of socially relevant and beneficial applications, and we're going to talk about one right now with Pranav. But it's really easy to veer into problematic territory, even if we're not trying to do anything bad. And it's important that we, as the AI engineers who have the power to create these systems, understand the dangers associated with training models without having any sort of foresight. And it's our responsibility to make sure that when we train these models, that it has certain assurances before they're sort of deployed to end users. On the technical side, we learned a little bit about how to do gradient descent, what a neural network is, what logistic regression is, and how to engage in gradient descent using computing gradients using loss. And we learned how to add more layers to create a deeper neural network. Okay, in case there are any other questions, I'll stop one more time. Any more questions before I move on? I do want to move on to Pranav and let him share his interesting research. So if anyone has any more questions, please feel free to reach out to me or Karan. We'll give our contact information. And there's always, the further workshops. But I want to pass it off to Pranav. He is a researcher at Stanford. He did his PhD there, and he's done a lot of work in applying AI and deep learning to medicine and healthcare. And so he's going to talk about that right now. So everyone, please welcome Pranav. Do you want to share your screen now?
Hey, thanks, Shubhang. So let's see, let's get my screen share going. All right, awesome. Hopefully you can see my screen right now. So great to be here. Thanks all for attending. Shubhang spoke about the responsibility of those who are developing AI to make sure it's being used for good things. And I can't think of another domain that has as much potential for great application of AI as medicine. And if we just look at the field of AI for medicine over the past 3 or 4 years, there's really been an explosion of the kinds of the kinds of things people are doing, both in research and in industry. And we're seeing some of this transition happening from these being research projects into these being technologies that are applied on real patients. And to give you a gist of some of the things that are going on, we have these methodologies being applied to medical records to make recommendations to patients or to predict a patient's prognosis or their health in the future, looking at claim forms and being able to tell how at risk a particular patient is, but also looking at signals, looking at ECG data, which you can now acquire from an Apple Watch and be able to tell whether someone has some kind of a serious abnormal heart rhythm. And of course, look at imaging. So here's an image of the brain, and there's been so much work done in imaging over the past few years that I really think it's where we will start to see one of the first applications in the clinic of modern AI technologies. I just wanted to share a few examples with you. And these have been some of the most exciting pieces of work in the past few years. And I want to show you how far we've come in just a few years. So this is back in 2016. One of the studies that really kicked off this whole field was this particular study by Google, published in one of the most prestigious medical journals, which looked at these images of the retina, they're called retinal fundus photographs, in order to determine whether patients who have diabetes are going to suffer a complication of diabetes, in this case, leading to blindness. And this is the leading cause of blindness for adults. And it can be diagnosed by looking at images of the retina and then being able to spot that this patient has what's called diabetic retinopathy. And then since then, the explosion has been applied, really has been seen across various fields in medicine. So the second is an example that came out of Stanford, actually, by Sebastian Fern's lab. And this is looking at pictures of the skin and determining whether the skin lesion is malignant, in which case there needs to be an intervention, or it's benign, so it can just be left alone. And this is very critical because often, you might get a mole and you might go to a dermatologist, and the dermatologist is tasked with doing this determination. But in this study, they showed that that one of these machines, one of these AI solutions, could do it as well as dermatologists can. And then the third slide is the third image over here is an example of a whole slide image of a lymph node in the breast. And here the task of interest is to tell whether cancer has spread to the lymph nodes. This is important because that's one of the ways that doctors are able to decide whether cancer has progressed onto its later stages at which more aggressive treatment needs to be performed. And here's another task, another field in which we have these algorithms perform as well as doctors. So that was really cool. And this is just 2016 to 2018. People were shocked by these results. No one will be shocked by these results now because across a wide variety of fields and tasks, it's been shown that this is possible. So what's really 2018, 2019, and 2020 been about? It's been about the translation of these technologies from being mere research projects to things that are actually close to being used in the clinic. For the diabetic retinopathy work, in 2018, there was the first FDA authorization of an AI that can act completely by itself without any physician oversight. So this is really big because it's saying that we don't need these to be tools that doctors use necessarily, but we can use this as a first line where someone goes into Walmart and has a picture of their eye taken, and then the machine says, go see an ophthalmologist or don't go see an ophthalmologist. So that's been really exciting. And then what's really important is for us to be able to say, okay, these are doing good for patients in the world. And for that, in medicine, the standard is to do a randomized control trial where you say some of the patients will get the AI as part of their diagnosis. Here it was looking at colonoscopies and looking at whether one could find colon polyps. So this is, you can imagine polyps are these little sort of bumps on the inside of the colon that you want to recognize and remove. And these AI systems were actually shown to actually have a higher detection rate than if it was just a gastroenterologist operating by themselves. So that's been super exciting as well. This is some stuff that came out of the Stanford Machine Learning Group, where I've been a PhD student for the last 5 years. I've actually been in the lab for 8 years now, just having started as an undergrad. There's been a ton of work that's just come out of the lab in terms of looking at abnormal heart rhythms, looking at a variety of scans in radiology, and Shubhang also worked on one of these. And then also work in histopathology, looking at whole slide images, looking at EEG signals to determine whether a person with depression will respond to a certain kind of treatment. So there's been a lot going on just even at Stanford in our lab and beyond our lab as well. And the work I'm about to share today, there's just a ton of work that goes into it. So it really takes a village to get some of these things to the stage at which they are at now. And today I just want to focus on chest X-ray interpretation and give you a flavor of how the thought process in terms of developing these technologies takes place and how that evolves over time. So I'll just start by giving a little bit of context into chest X-rays and why they are such why they're such an important, and also why they have been so much the focus of a lot of work that is coming out in the last few years at the intersection of AI and medical imaging. So one is that chest X-rays are just critical for the detection of many diseases, pneumonia, TB, lung cancer. These affect millions of people. And then this is one of the most common diagnostic imaging exams. There are 2 billion chest X-rays that are performed every year. That's crazy. And it's super valuable to automate. Why is that? It's because one, if you're in a developed country, one of the big problems with this is that radiologists can make error while they're interpreting these images just because there's so many to interpret, and radiologists at the end of the day are people, they're subject to fatigue, biases leading to errors, and we can hope to address some of these errors with the introduction of automation. We can make it worse as well, but we'll chat about that further. And then the second important statistic here is that just 2/3 of the world's population does not have radiology access. And that's crazy to think about, is that in some parts of the world, there's a couple of countries where there are fewer than 10 radiologists in the whole country. And these are countries that contain millions of people. So that's pretty big if we're able to automate in those regions. The important thing here is that it's not just useful to have something that kind of works. It needs to really work. And more specifically, we can give it the target of saying this needs to work at the level of expert radiologists for these to become things we'd consider using in practice. And that's a high benchmark. So I want to just structure the next 2 segments as follows. One, I want to show you how some work done from 2016 to 2018 got us to show that we're able to build these machines that achieve the same performance as radiologists. And I want to share then some challenges in terms of the generalization of these algorithms to real-world clinical settings. Okay, so this is what a chest X-ray looks like. Here's what a normal chest X-ray looks like. You're able to see the lungs right here. So there's the left lung, there's the right lung. Here's the heart. And the basic idea behind what you see in a chest X-ray is if there's air, then air appears dark. If it's bone, that appears white because it's just reflecting a lot of radiation. And tissue is sort of in the middle. It's neither white and it's not black, but it's grayish. And that way, a radiologist looks at this image, looks at the different anatomical structures, and is able to say this chest X-ray looks normal. But in order to show you how this is normal, maybe I should show you an image that's abnormal. So here is a radiology finding called consolidation. Consolidation is when fluid builds up in the air sacs or the alveoli of the lung, and now you no longer have air there, you have something else, which might be pus, and therefore the X-rays are not going to go through and create a sort of black image. It's going to have these things that we call opacities that represent a particular disease. But there's not just one disease. You care about identifying multiple diseases here. So here's fluid in another part of the lung. Here it's called pleural effusion. And here's another one. So here's a nodule, and nodules are found on chest X-rays, and these are little lesions that can evolve into cancer, and therefore must be looked at regular intervals to monitor how they're changing over time. But to add even more complexities here, there's not just one type of chest X-ray. You can have multiple types of chest X-rays, and your algorithm needs to handle each of them. And then a chest X-ray, this one's from the Stanford hospital, of a patient that's admitted into the hospital, actually has many, many different pathologies. It's not good enough to be good at one of them. You really need to have the understanding or the ability to have your algorithm be able to say everything that's going wrong with a certain chest X-ray. So the field of automated chest X-ray interpretation has a long history, as do many research subjects. But really, there was a flip in the field in September 2017, when there was a large data set of chest x-rays released by the NIH, and this was over 100,000 examples. And each of these examples had annotations of what was contained in that chest x-ray. So you might have examples for each of the pathologies that we've talked about. And the way the deep learning algorithm works, Shubhang gave an example of, is you provided a input, you provided an output, and you say, learn the relationship between the input and the output. So here I give an image which contains a nodule, and it goes into my deep learning algorithm. Here's another one that's a chest x-ray that is normal, and that goes into the deep learning algorithm. And you feed in enough of these, and eventually you're able to get an algorithm that will take in a chest x-ray and output the likelihood of several different pathologies that may or may not be present in that chest x-ray. Now, the process of developing a chest x-ray algorithm consists of three things. One, you pick a neural network architecture. Second, you pick an optimization strategy. And third, you pick a regularization strategy. Now, it's not important to really understand what these are if this is your very first introduction to deep learning. If you know what these terms are, then this is a particular type of convolutional neural network. This is a loss function, which is a variation of the loss function that you saw today, except now you have a sum over the 14 pathologies. And a regularization strategy here is data augmentation, which just says which says rotations here, your model should be invariant too. But if this is your first exposure to deep learning, you should really think of it as playing Mario. You have wheels you can select, you have flights you can select, and you have a body frame you can select. And it's really quite difficult to get these right the first time that you're playing Mario, but eventually you understand what's right for the track that you're on. And that's how I would describe the deep learning experience as it remains to this day. So we did this search, and we found that at the time our algorithm achieved superior performance. We compared it to all previous approaches and found that across all of the pathologies, we were outperforming previous approaches. And I won't get too much into how we did that, but I think one of the key evaluations here is that it's not just useful to compare against what people have done before. What's really useful here is to compare against how experts would do on this task. So how do we do that? So first we say, let's ask a group of radiologists to label a certain set of chest x-rays. We're going to call that the test set ground truth. And then what we're going to do is we're going to set up a competition between a radiologist and a machine. And here we're going to have 9 radiologists just so that we're sure we're not biasing ourselves with any one radiologist. And then we can compare them to each other. So here we have the algorithm in blue, and we have the radiologist in red, and we're able to compare the two bars and see whether the algorithm is performing better than the radiologist. So what happens here? We see that the algorithm performs comparably to radiologists on many tasks, like 1, 2, 3, 4, and it performs worse on others. So you might ask the question, why does it perform better on some? Why does it perform worse on others? And one hypothesis that we have here is deep learning algorithms require a lot of examples. Let's just see if the number of training examples matters. So we look at the categories for which we have a lot of data. So here in yellow is the amount of data we have. And we see for atelectasis and effusion, we have a lot of data and the algorithm's performing as well as radiologists. Great. And when we look at pneumonia and hernia, in fact, the yellow bar is so small you can't even really see it. When we look at these pathologies, we see that there is a difference between the two. But here's some weird cases. In infiltration, we have a lot of examples, but we're not able to see the algorithm perform as well as radiologists. But on edema, we see that the algorithm does perform well. So that's interesting. So it can't just be the number of training examples. There must be something else. We thought, okay, it's not only about the number of training examples. There's probably a relationship between how well these pathologies are labeled for. If it's true that maybe the label quality is really high for some pathologies, that we're able to detect them better. And so here I'm about to show you what the label agreement is with the ground truth. So a higher number is more agreement, a lower number is less agreement. And we can see this explains the difference. So we have very few examples, but high agreement, and we're able to do well. A lot of examples, but very low agreement, and we're not able to do that well. So there's a relationship between number of examples you have for something, but also how well these examples have been labeled for. And that's very important, especially in the context of medicine. So we did this. We found that our algorithm performed as well as the radiologists for 10 out of the 14 diseases, performed better than the radiologists on one disease. And this was very exciting at the time. We got covered by MIT Tech Review, Wall Street Journal, Vice News, made it on Forbes and Time. Just kidding about those last two. I wish we made it on Forbes and Time. But it's not ready. And it's not ready for clinical practice because even at the time we knew that, okay, this study is valid and it makes sense and all our results hold. But there are quite a few technical gaps between showing that we achieve radiologist level performance in a control setting and saying this algorithms will generalize in the clinical setting when applied to real patients. And I want to show you some examples of this technical gap that we have. So just at the time at which we were completing the study, this was November 2018 now, there was a study that came out that said, you know what, these algorithms are not as good as we thought. And here was their experiment. They said, let's train on a hospital, let's train a model, let's find out the performance on that hospital, and then let's find out the performance on another hospital. And you can see that there's a drop. And you can repeat this experiment the other way around. I'll say, let's only look at hospital 2, train a model, and let's look at performance now in hospital 2 and how it generalizes to hospital 1. And again, there's a drop. So what is this saying? This was getting at, okay, you apply things to another hospital, it just doesn't work that well. And it's really hard to try to think about why this might be. Now, is it because your patient populations are different? Is it because the difficulties of the data set are too different? Now, it could be either of those two reasons. We had a third hypothesis in mind, which was that these chest X-ray data sets are just very noisy, and we shouldn't really trust the label that we're getting for these data sets. And there had been others at the time who had also highlighted some of the problems with these data sets, saying, a lot of these examples are mislabeled. I would not label it like that at all. And so how do you reduce this label noise? And label noise is going to come up a lot in medicine because unlike in the general setting, you ask two people whether something's a cat, people will generally agree. If you're in a clinical setting, you're debating whether something's some subtype of some type of medical disease, and you've got a lot of disagreement. So how do you resolve that disagreement? You can collect a strong ground truth. You can say, let's put a bunch of clinicians in a room together, let them figure out the test set annotation. But then if you want to train a deep learning model, you just can't do this for 100,000 chest x-rays. You can't get radiologists in a room together and say, you know what, you're going to sit in here for the next 10,000 hours until all of our data set is labeled. It's just infeasible. So what do we do there? So idea here was to develop our own data set and see if we can make it better labels. And we call this data set Checkspert. Now, if you've been noticing the naming scheme, there's a lot of checks in there, and semi-proud of that. Some people just do it better in Silicon Valley. So hopefully I can plan it to have a lot of context around how these have been named. Okay, so just to chat about this X-ray data set that we decided to collect. At this time, this was going to be the largest chest X-ray data set that was going to be released to the world. And the idea was to have very, very clean labels. So this is a deep learning workshop. And so I just don't want to talk just about computer vision. I want to give you a little bit of insight into what goes on in natural language processing as well. And so I just wanted to include this section of how do we actually label chest x-rays with their associated diseases, saying this one contains this disease and not that one. And the way it's done in the field is they're actually labeled using natural language processing on the radiology reports. So what happens is for a chest x-ray, you might have a radiologist who writes a report that says, here's what's going on the chest x-ray. And then what we do is apply a report labeling natural language processing system that says, this report contains atelectasis, it doesn't contain cardiomegaly, it doesn't contain edema, and so on and so forth. And we looked at the existing natural language processing tool that was there, and we just looked into where it was making errors and improved upon it. So I just wanted to include this as a slide to show that applying artificial intelligence is sometimes not about these very sexy, just new deep learning methods that are transformative. Sometimes it's about understanding where things are not working right now and what are small tweaks that you can make to make these things work well in practice. And that's what this particular exercise was in. More recently, we've been looking at how we can employ some of these sexy advancements in NLP in the last year, and we're looking at whether we can combine rules-based systems with BERT-based labelers in order to improve these further. And we've shown that we can improve significantly the performance of these NLP systems on a wide variety of diseases. Okay, here's an example of where a deep learning system does pretty well. So one is when we're looking at a pathology called cardiomegaly. So this is an enlarged heart. And you can see this radiologist actually misspelled cardiomegaly. They missed the D. And turns out that if you have a deep learning system, it can actually pick up when spelling mistakes have been made. Similarly, here's an example of a radiologist conveying that that this particular disease is unchanged in appearance. And the original system said this disease doesn't exist, when in reality, the idea is this disease may or may not exist, but all we know is it's unchanged, so we mark it as uncertain. There are a lot of these subtle things that you can get right with deep learning systems in terms of handling edge cases. So we did this. We had a good labeler. We opened up the data set. It was the largest data set at the time. And we just set up a competition where we said, if you have a chest x-ray model, you can see how well it works. And we had our baseline model. And this was a collection of 30 models. We were training this for days and days and days. And it's now number 73 on the leaderboard, just in 1 year. And there have been just a ton of people that compete and sort of know how to build good models here. And just the best models are performing really, really well now compared to radiologists. So I want to come back to a previous point. I had talked about how we had seen this paper that had showed this decrease in performance when you move to hospitals. And we had thought if we just created a better data set, we'd be able to solve this problem. So now we did create a better data set. Did we solve this problem? And so we looked at some of these models now that people have submitted and looked at, okay, do you actually now see a drop in performance? So you train on the Chexpert data set, and then you apply it on another data set from a different hospital, and you can see, okay, there's a drop in performance. But you look at another disease, and you see there's actually an increase in performance. And we were just scratching our heads here. How can you have an increase in performance when you go to a different hospital? And we were stuck on this for quite some time before one of the members on the team suggested, why don't we look at what happens with radiologists? Do they also have a difference in performance as you're going from one hospital to another? And so we did this experiment. We said, here's the model in blue, here's the radiologist in yellow. Let's just see across the different diseases, does the model have a difference in performance, which is also reflected by the radiologist? And this just makes a lot of sense now, that if we do see an increase here it might be because this hospital's cases are just easier and a radiologist also gets better. Or cases for cardiomegaly in this other hospital are just much harder. So both the models and the radiologists suffer. So there's an important takeaway in terms of measuring generalization is that you care not only about how the models generalize, but also how people generalize. So I talked about this cross-institutional generalization gap between taking these from the lab setting out to the real world. I just want to share one more shortcoming of models that is particularly relevant now. So could models detect pathologies unseen in training? Well, gee, what's a pathology which is unseen in training? COVID-19. So there's been a lot of controversy over whether chest x-rays are the right thing to be looking at for making a diagnosis of COVID-19. And there's a lot of controversy because there's a lot of differences in the way this has been implemented. So the CDC did not recommend either chest x-rays or CT scans to say someone had COVID. But at the same time, in Spain and in UK and Italy, there were several hospitals that were just out of testing kits that were actually using chest x-rays to determine whether someone had visible signs of infection that then they could use to say, you definitely have COVID. There's been a lot of developments on this that I won't get into right now, but the one study design flaw that I want to talk about is the following, is that a lot of people, what they tried to do in these studies looking at AI to diagnose COVID-19 is you have positive cases from, let's say, a hospital in Italy that's decided to change, that's decided to share their data set. And then you have negative cases from a hospital at Stanford that's never seen COVID at the time. And then you say, okay, I'm going to merge these two data sets. And what I'm going to do is I'm going to see from an x-ray, can you tell whether this is COVID positive or negative? And people just reported crazy scores. People were reporting, I can tell with almost perfect result whether this is a COVID result, whether this is a COVID x-ray or not. And there's quite a subtle flaw here, which is it's impossible to distinguish in certain cases whether what your model is picking up is whether you have COVID or not, or whether it's picking up whether your x-ray is coming from Stanford or from Italy. And one test of this, which was really funny, that one group did was they said, let's just crop out most of the chest x-ray. There's no way you can tell because you've cropped out the lungs now. And let's see whether the model still does okay. And turns out this model got almost perfect accuracy. It just was able to tell. So that's one of the flaws that highlights how important it is to actually engage with the domain and really understand some of the subtleties and the challenges with some of these study setups. And I think that's why it's important to have this infrastructure where you're able to immerse yourself in teams that do this. Okay, my final generalization story is going to be on detecting pathologies in smartphone photos of chest x-rays. Now, why is this important? It's because most of the world actually still uses chest x-ray films. So you get a chest x-ray, it's on a film, and you can literally take it home with you in a lot of countries. And there's no way to directly apply a model to your film, which is in your hand. So one way to digitize this is to take a photo. And this is a nice solution to scale deployment. But one thing we don't know is whether models actually work when you take photos. And so we did an investigation where we looked at a lot of models and we asked the question, okay, now if I apply them to photos of these chest x-rays rather than to chest x-rays themselves, do they have a significant drop in performance? And the results look encouraging. So there's still preliminary results, but they show that there's somewhat of a drop in performance. So the blue is the original performance and the gray is the original performance, the red is the photos performance. You can see this tiny drop. Now, it turns out this tiny drop is significant in that you might lose one patient's life or misdiagnose one or two patients out of 100, which you might be concerned about, but it's not like you would start misdiagnosing everybody. And this is a very active area of research right now. and one which we're paying close attention to. But the idea here would be the following, is that you could simply snap a picture of a chest x-ray and then upload it on the cloud and get a feedback of what the probability of certain diseases is and what a heat map over the image looks like. And this is very possible to do. So just to wrap things up, the first part of excitement in AI for medicine has really been about the development of these algorithms that do as well as experts. But really the exciting challenge right now is to tackle all the technical challenges to get these to work. And of course, the challenges are beyond the technical. There's also a lot of legal challenges associated with this. There's a lot of ethical challenges that are associated with this. So there's a vast amount of work that's necessary to make this transition, but this transition, I believe, will really happen. There have been a lot of people that have been involved in the work that I've shared today. And I just want to acknowledge everyone that's been a part of this. I just wanted to end with a few resources in case you're interested in keeping up with the field. So this is one resource which you can subscribe to. It's a weekly newsletter which I write. That just shares the latest papers that are coming out at the intersection of AI and healthcare. And this is one good way of keeping up to date, especially if you have some background in AI and healthcare. At some point, I had just built up just a stack of notes on what it takes to get up to date on everything in terms of AI for medicine research if you do have a background in AI. And last summer, I decided to spend some time just turning it into a Coursera course with Andrew Ng's support. And so that's now online, and you can check that out if you'd like. And then finally, there's the AI for Healthcare Bootcamp, which is a 6-month program that we run in the lab. And this is a bunch of where all of the projects that you saw today come from. And it's a ton of fun. And the applications are now open for the fall. And I'll end there. I think we just have a very short few minutes for questions. So maybe we'll do those. Or actually, maybe Shubhang, whatever you'd like.
Yeah, well, thanks so much, Pranav. I like to do this really corny thing that embarrasses people, which is I ask people to mute themselves and clap. Although no one can unmute themselves, so that's going to be really embarrassing. Wait, hold on. Unmute all. Ooh, okay. Okay, that was very embarrassing for everyone involved. That's great. Okay, so we do have some time for questions. If people want to ask questions, feel free to ask some questions. Quick things I want to say really quickly. Thanks again, everyone, for coming. And we're going to post the recording. Going to post the slides. Going to post the... Hold on. Going to post the solutions to the exercises as well. And we'll send an email about that. And then hope to see you next week as well. So thanks again for everyone for coming. And now I'll turn it over to folks for questions. Feel free to use the raise hand feature again, and we'll unmute you, and then we can have Pranav answer some questions. I think there's some questions in the chat.
Oh, well. Cool. Yeah, I see some questions in the chat. Maybe I'll start with those while people are thinking of questions. So could I elaborate on possible edge case? Then I think this probably was a question on the natural language processing tool. So I guess two sets of edge cases here are, how do they handle misspellings? And number two is, how do they handle ways in which radiologists specify uncertainty and negation of certain pathologies? If you say, this may be disease X or disease Y, one should be able to capture the uncertainty there. Cool. So the second one is, there are many parts of the world where radiologists in short supply. Would a neural network be better than anything? I think here it's important to ask, what's the standard of care? If the standard of care is the physician who takes the chest X-rays responsible for the interpretation, then I think the comparison, it makes sense to have with the with the physician and see if the algorithm is at least as good as the physician. There are a lot of ethical challenges here, especially with who's able to use the app and who's able to make decisions. Because at the very extreme, what you can do is, if you're a patient, you can just come home and put your chest X-ray on your wall, snap a photo, and then make your own judgment, and then call your doctor and say, "Hey, I noticed this algorithm picked up X. Why didn't you say anything about it?" So there's a lot of ethical challenges there. Okay, there's a few more questions. Does it help to understand the biology behind medical conditions? Have you taken classes in the medical field or projects like this in collaboration with medical professionals? So thanks. Yeah, great comment. I think it helps to have I think it helps to deep dive into whatever domain it is you're working in. And this is not just true for medicine. This is true for even other things that I've worked on. Like when I was an undergrad, I worked on autonomous driving. And there it was very, very useful to understand how cameras were calibrated. It's just a small thing, but it makes so much difference to an understanding of sort of how you wanna solve a particular problem. And medicine is not an exception here. It's very useful to be able to dive into that domain. One of the things I'm very grateful about is Stanford Med School being next door, and a lot of these projects have been done in collaboration with a lot of people in the med school. So it does help a lot to have someone on the team who really understands that. Next question, and I guess maybe I'll just take two more, the ones that are already on there, and then I'll hand it back to Shubhang. So the second last question is, what are ethics concerns that come up in your work? Do you find that the healthcare industry is largely receptive to incorporating ML technologies? So some of the ethical concerns that come up in the work is surrounded around one, replacement versus augmentation, which is we're building a lot of these models to do essentially what a radiologist does. What is a structure in which we can not replace the radiologist? I guess there is no radiologist who would like to adopt a system that's ultimately repeating their work. So is it actually going to help improve whatever that is that they're doing? Other ethical challenges come up around fairness of these systems as well. Little is known about the fairness of these systems, especially the data sets that they were trained on. There seems to be a balance in terms of at least gender that's in this data set. One of the challenges is with age. Some of these algorithms really shouldn't be applied to kids because just anatomically kids look different. And so that's one of the ethical challenges, is sort of what population should I be comfortable applying this on and what population should I not be? The healthcare industry is somewhat receptive, somewhat not. And I think the somewhat not receptive part comes from that. What's the alignment in terms of incentives for the hospital to adopt this? Sure, patient outcome improvement is one outcome, but if you're to demonstrate that this could save cost for the hospital, then there would be a lot more people that would be interested from a hospital's perspective in terms of adopting these technologies. And some of these transitions have not been made in terms of these demonstrations. All right, final question. How can you get patients to trust more invasive medical AI, such as those that do surgery? The same way that you get patients to trust drugs that we know nothing about their mechanism about, is that we have RCTs demonstrating that these do improve patient outcomes and these do not have side effects that that patients experience. So I think it's the same way. There's a little bit more of a real-time aspect to this than I guess drugs do. And in that way, I think this question is very parallel to in the autonomous driving setting. How do you trust passengers in an autonomous how do you make sure passengers in an autonomous car or bus actually trust the machine that's driving it? Okay, I'll maybe stop there and just thank everyone for coming in, for Shubhang and Karan and the organizers for inviting me. Thank you.
Yeah, thanks so much, Pranav, for coming and giving this fantastic talk on your research. And thanks to all of y'all in the audience for coming. We were super excited to host this. And we hope to see you next time as well. We have all of your emails, so we'll send another email about next time as well, where we'll be doing more of a deep dive into computer vision and some aspects into racial bias in computer vision systems. So thanks everyone for coming. And if you have any other questions, feel free to shoot it at me, and I'll send a follow-up email with all the materials very shortly. So thanks everyone.